Housekeeping. It's now my privilege to be able to introduce our first plenary speaker. Tony Hay is now the Senior Data Science Fellow at the eScience Institute at the University of Washington. But Tony's had a number of other posts over the years, and in particular, one of the reasons why we asked him back is that a number of years ago, he, along with a number of other people, when he was running the eScience program in the UK, saw the need for an organisation at national level to address some of the issues around digital curation, around making information reusable and reinterpretable by others, those others than those who'd curated it. And it's thanks to them and thanks to their bringing together two streams of funding from two different sources that created an organisation in the DCC whose remit encompassed both service in digital curation and research in digital curation, that we ended up with the organisation that we did today, and that organisation that decided that one of the things it needed to do was to run an event like this to bring together people with common interest in issues around digital curation. Tony, I'm sure, is going to give us that perspective, both from the minds of those who saw the need to create the DCC 10 years ago, and indeed looking ahead, hopefully, to the challenges that still remain, as well as the achievements that we've seen. So I welcome now to the stage, and I'll ask you to join me in welcoming Tony Hay.
Thank you very much, Kevin. That's great. Well, it's great to be here. Yes, I was at the giving a keynote at the first Digital Curation Centre Digital Conference in Bath, I think it was. But fortunately, my curation habits are not so good, so I couldn't find the slides. So I'm sorry about that. But I do have some things to say. So let me, first of all, begin with a warning, just to tell you that this talk is a personal view. It doesn't attempt to survey all the great things that are going on. I see lots of things going on, but I don't attempt a comprehensive survey. So I apologize in advance if I haven't mentioned yours, but I'll talk about some of the ones that I see the continuity from what was happening when I was dealing with it in 10 years ago and where we are now. So it's not intended to be comprehensive, and I'm grateful to our large cast of people who've helped me and educated me over the years, but they're not responsible for my blunders in the talk. And I would just like to point out one of my colleagues who unfortunately died, Lee Dirks, was one of the people who educated me most in this subject. Okay, so having apologized for the omissions, let me start with the past. So I will say a little bit about the UK eScience Initiative, which was a 5-year initiative, 2001-2006. I'll produce a slide from 2004, which I think is very interesting, and then what was going on in Microsoft Research with Jim Gray in these last two bullets here. So let's start with eScience. So it finished in 2006, but there was an international review done by a very eminent body chaired by Dan Atkins, who led the cyber infrastructure activity in the US. And it concluded that the UK eScience programme is in a world-leading position on the path of building a UK foundation for the transformative enhancement of research and innovation, a pioneering vital activity of enormous strategic importance to the pursuit of scientific knowledge. So it was pretty nice, all right? So actually we had done a lot of things in this country at a very early stage. What I think I underestimated was the time it takes for culture change to happen. So just to remind you what it was, there was around about £250 million, a lot of money from the government for universities and for collaborative projects with industry, which was, to me, a very exciting feature of the programme, and it involved all the research councils. So I'm apologising to our guests from overseas with all these acronyms, so I'm just explaining them once. Engineering and Physical Sciences is EPSRC, Biology and Biotechnology is BBSRC, Natural Environment, Medical, Particle Physics, Economics and Social Science, and Arts and Humanities. So there's a whole bunch of acronyms. And if you're on the US side, they're sort of equivalent, Research Council's UK equivalent to NSF plus a piece of the NIH, the National Institutes of Health, and the National Science Foundation. So these are the acronyms, and they were all involved. I have to say some of them were reluctantly involved. The vision of eScience was from John Taylor, and he was the Director General of the Research Councils, and he got money for this, and so they only got the money if they did it, but they would have preferred to have the money and do what they wanted, and it took them some time, I think, before they realized that this eScience stuff that we're talking about was actually core to the mission of each of these research councils, which I think they do now. This is a slide from 2004, which I gave a talk, and it talked about the 6 key elements of a global e-infrastructure. And it was interesting to look at this. Obviously, nobody disagreed with the high bandwidth network, authentication, authorization, and accounting infrastructure. Development centers for open software, we see that now happening in the US and in the UK and elsewhere. And obviously, discovery services and collaborative tools. Work on tools, making stuff easier to collaborate, easier to discover. But these two are interesting. Technologies and standards for data provenance, curation, and preservation. So I'd obviously been educated at this point. Open access to data and publications via interoperable repositories. And this was in 2004. Now, I've talked about the research councils. Actually, one of the jobs I had was running the eScience program for the research councils, but I also had another hat which was absolutely valuable in establishing the Digital Curation Center, which was that I was chair of the JISC committee for support of research. So it was actually not doing research, it was doing support of research, and that and the science program gave funding for the DCC. And so I would like to record our gratitude to JISC, which was, in fact, a very pioneering organization and a wonderful asset for the UK. So Digital Curation Center came out in 2004, and we see where we are now. Meanwhile, in the US, Jim Gray had realized he was a famous database guy. He's a Turing Award winner. When you go to a bank account and take money out of your account, this is the two-phase commit. He was one of the people responsible for that sort of technology, transaction processing. But he also realized, since the beginning of the century, he was working with scientists with their big data. He realized that was the next challenge. So he was working with astronomers, he was working with biologists, and so on. And so he came up with a very similar idea to eScience. We obviously have these two ways of doing science, experimental science, and then since Newton and Maxwell and so on, we can summarize that experimental data in laws of nature and do theoretical explorations and then make predictions which you can verify with experiment. And those are the ways we've done science for hundreds of years. But in the 1950s, of course, we invented computers. And that enables you to go and explore areas where you can't do the experiments very easily, maybe too hot, too cold, or whatever, too remote, or where you can't do the experiments at all, like climate change. We only have one climate, and galaxy formation. It's very difficult to do experiments on galaxy formation. So simulations of complex phenomena, and you need people to be trained in numerical methods, algorithms, parallel computing, supercomputers, programming, and all this sort of stuff. And those are skills in addition to the theory and experiment. Doesn't replace them. But Turing Award, it was a Nobel Prize winner, Ken Wilson, called that the third paradigm. Jim Gray introduced the fourth paradigm, which is now you need to worry about large amounts of data. That's going to be overwhelming scientists coming from high throughput instruments like gene sequencing, supercomputer simulations, sensor networks, satellite surveys, and so on. All these things are resulting in a flood of data, a deluge of data, I think was one of the papers that I wrote back then. And he called this the fourth paradigm, that you need to train people in how to schema, what metadata is, how to manage data, how to move it around, how to curate it, and so on. And eScience, my view on eScience, that it's the tools and technologies to support this sort of collaborative, data-intensive science. And So I think this is an enduring thing, and eScience will actually just be the way we do that. So I think the data-intensive science is in fact a new phenomenon, where you actually go and look at the data, not necessarily with a hypothesis. And this is an interesting slide that when I went to Microsoft, there was a supercomputing meeting in Seattle that year, and I'd been invited to give an invited talk. And then I joined Microsoft, and so the organizing committee wrote back and said, Tony, very sorry, but we've now got 2 speakers from Microsoft, so we'd like to take away the invitation to you. I said, why not take it to the other guy? Well, the other guy was, of course, Bill Gates, so they didn't do that. Anyway, but this is a slide from his talk, which is, to me, very interesting. It's a sort of executable paper where you can go to the data, you can actually go and play with the simulation, you can look at the visualization, new ways of collaborating. The whole electronic journal is a dynamic document. So we're getting towards there, we're not there yet. Okay, so that's where we were. And then in the next 10 years, what have we been doing? I like to look at some of the projects that I knew most about. So I'll talk a little bit about astronomy, bioinformatics, chemistry, and environmental science, which I know a little about, all of these things, and a project in the US on ecology. And then I'll talk about big JISC and little JISC, and one of the example overseas initiatives from Australia, which is a very serious activity. There are other ones like in the Netherlands, DANS is another example I could have taken. And then the whole agenda of open access, open data, and open science. So astronomy. So Jim Gray was working with astronomy data. He was working with astronomy data because, as he said, it had no commercial value. So nobody was going to worry what you did with it, you could just do what you liked. And he was sitting in meetings, you've all been in these meetings, interminable meetings discussing if you do this, do that. It was the National Virtual Observatory Consortium, and they were discussing what data, what things they should do. And he got really bored with this. So one summer with Alex Zale, astronomer at Johns Hopkins, and a couple of graduate students, they just put the data up online as one of the first web services. And so this made a huge difference, huge amounts of data, great public interest, millions of people looking at it. There are only 10,000 astronomers, so the public was really genuinely interested. It led to many scientific publications. It was a different way of publishing. You put the data out there with 300 million galaxies. You can't analyze it all before you put it out there. And you could engage some citizen science with Galaxy Zoo and so on, as well as serious science and education. So it was a great project, they just turned off the imaging camera in 2013. So it was a 20-year project. But for this purpose, what are you going to do with the data? Well, actually, they've just, NSF, under its Advanced Cyber Infrastructure Program, had this initiative, Data Infrastructure Building Blocks, and it funded a long-term access to the Sky server data in 2013, 7.6 million, a 5-year project, which would enable it to be usable and accessible for years beyond that. But the only point I want to really emphasize here, it's not just the data. What they'd done with Sky Service was they'd actually have a number of services that the astronomers could go and get from the data. And when the technology changes and all these things in the last decade and more, you need actually to curate not only the data, but also the services life cycle, because things change. So data and services are the function of this, and also besides these big astronomy things, there's also looking at this long tail where small data sets, individual scientists are producing data. Okay. What happened to virtual observatories? I told you Jim Gray got bored. Well, actually, so did the funding agencies. The big project in the UK was AstroGID. It was discontinued in 2008, and the virtual observatory in America was discontinued in 2014. This sounds terrible, but actually it's not so bad, because much of the infrastructure tools and the data archiving is being done, in this case by NASA, and so much of it exists, continues, and lives on. It's just the way it's funded is different, and they're still participating in the International Virtual Observatory Alliance, which is a very useful standardization body, and I'll come back to that. Astrophysicists are also very good. They have a number of systems that are the envy, I think, of other fields. They have a thing called the Astrophysics Data System, slightly confusing because it's about journals, not data. It's a sort of access to the actual full refereed article. You can go and get it. You can go to the journal. You can find out what the abstracts and so on. But you can also link to the data. You can link to the various objects, and I'll come back to that. So this is one of the services run from Harvard, has been run for 20-odd years. And it links up with this. The data of these big telescopes is usually well curated at the telescope itself. And so that's where the data is actually held. These are, if you like, catalogs because they don't actually have the data. They have the indexes to the publications and also to the data. And what these do, the CDS, Centre de Données Strasbourg, is they run a number of services, SIMBAD. So in different astronomers are slightly strange people, by the way. They classify each other by wavelength, all right? So you infrared astronomy, visible, ultraviolet. And actually, if you want to find an object in this, is it the same object as that? Well, that's the sort of service that SIMBAD can give you an added value service on these data sets. And there's also a Visier catalog. So they have a number of services which offer extra value to these things. And this is a sort of ADS view of the world, I might add, but here's ADS in the middle. You have Visier and SIMBAD, these services, libraries, materials, and conference proceedings. You have the archives of the actual data at the instruments. You have the papers in the archive repository, journals, cross-ref metadata, and it all comes together with ADS. That's a slightly ADS-centric view of the world. There is an interesting problem. This is an interesting paper by Pepe et al. In 2012. The green and this is the total number of links to data in astronomy publications. So if I take 2001, what the green and the grey shows that 44% of the links of the data in these journals no longer work 10 years later. So actually, you can go to it and it links to data, but the links are broken. And so that's going to be a problem. How can you do better than that? So I asked Michael Kurtz, who was the originator of ADS, what his view of the future was. He was somewhat pessimistic in the last 10 years that he hasn't seen a lot of progress. One step forward, two step backs. He was worried about the virtual observatory because he thought it was too bureaucratic and wasn't dealing with the needs of users in a sort of lightweight way, and it has collapsed. He saw these new repositories like Zenodo and Dataverse creating lots of data they're saving, but really uncurated data, and he feels very strongly, as I think most of you will, that the value is in the curation. What he also said was the problem with curation is that the funding is typically local, but the data can be global and the use can be global. And so you have this sort of tragedy of the commons where nobody's prepared to pay for it. And I think that is a problem. And what I like, for example, about arXiv, where the publications are put in by astronomers and physicists, is that they have a sort of sustainability model. The arXiv is held at Cornell, but they charge universities for the use of that, a few thousand, and that gives them a budget to actually survive. This is, however, a slightly more positive view from Francoise Genova, who runs CDS. She thinks certainly the virtual observatory framework coming from IVOA, which all nations have agreed, has been extremely valuable. Interoperability framework helps the data producers share data so they understand what they have to do. So she believes that's been very valuable. And she also sees a lot more long-tail data. So these observatories, they have their big data sets, but there's individual astronomers with small data sets, and now they're attaching them to papers, and they're seeing more data attached to publications. In terms of numbers, they were one particular journal, there were 200 papers with a catalogue. Now that's gone up to more than double in 9 years. Fluid and 40 catalogues has gone up to 200 in 2013. And what they're trying to do at CDS, she's trying to develop services, instead of just the big data, can you develop services for the small, long-tail data science? Bioinformatics. Okay, so that's an important area, and one of the projects we had in the UK was called MyGrid, and it was PI was Carol Goebel at the University of Manchester, and she was working with bioinformaticians. And it's a very complex problem, as I'm sure you all know, because unlike particle physics, they have a lot of data, but it's all of the same character. In this case, you have gene sequences of letters, you have microarray gene expression data, which tells you what what protein is expressed by what gene, and then you have the sort of pathways, then you have the protein structures, and then you have how do you stop with the gene defect, how can you stop that producing bad effects in people? And so huge amounts of complex data to get from data to information to knowledge, information you can act on. So that was the scope of the project. One of the things that they focused on was what was workflows. So you actually have the original data, then you do various things to it before you actually publish it. And you need to know what's been done if you really want to be sure you can repeat it. And so they have this provenance trail done by workflow, and they were using the Taverna workflow system. And that's one of the things that they had a platform for which you could share workflows. And that led to a second project called My Experiment, which was a sort of informal where people could actually share the workflows, the provenance of where they got their results from their data, and other people could use the same workflows. So that was a sort of informal social activity, and it was meant to sort of, this is the water cooler, everybody meets around the water cooler and exchanges notes not only on what happened in Coronation Street, but actually about the next technologies and so on. And so that's what they were trying to do. They were trying to reproduce a sort of virtual water cooler for people to chat and have ideas around. And then there's a sort of do-it-yourself activity, the My Experiment. And this was another European project with EBI, that's the European Bioinformatics Institute near Cambridge, and it was to do a much more professional job providing a curated catalogue of life science web services. And so the picture you have is that you have social curation, self-curation in the My Experiment sense, but you also have this bio-catalogue, which is complementary, which is curation by experts and automated curation. So that was the sort of things that have happened. Some of them, there's lots of other things that have happened, but that's one of the things I wanted to emphasize. The other thing I want to focus now on a professional service. This is EBI at Hingston. What they do, labs send data to them, they archive it, they classify it, they share it with other data providers, they analyze, integrate, and provide tools to help people use it. So what does that actually involve? Let's look at one of their databases. And this is, if you like, the gold standard database on genetic stuff. It's called UniProt. And so Rolf Apweiler, who is the curator in charge, these are his numbers, 100 FTEs on just this one database, with around 40 full-time curators. He makes the point that purely archival database, you just stuff the database there and people can access it. That's fine, has minimal metadata, but it doesn't have the annotations. And if you have the annotations, annotated databases have millions of users. UniProt has at least 4 million users. So it's many more than the tens of thousands. The literature used to do that curation, they pick up results from, he estimates 10,000 papers a year. The research funding that is provided to produce those papers is around €1 billion, so it's a lot of money, for the papers. And so the full costs of UniProt, which are around 12 million a year, are very small compared to the cost of the research that they take account of and the number of people who are using it. So it's an argument for the cost effectiveness of serious data curation. But there is a problem, and it's really a crisis in bioinformatics in that the non-reproducibility of some of the results. This is just two statistics. 2,000 articles were retracted from PubMed in May of 2012. 20% were retracted because of errors. 67 were retracted because of misconduct. 43% of fraud or suspected fraud. People have done a duplicate publication. They published it in many places, 14%, and plagiarism, 10%. a serious worry, I believe. But this is the one that really upsets me. Companies like Bayer and Amgen had concluded when they tried to reproduce the results of papers published in things like Science and Nature that 60–70% of it may be non-reproducible. And there's a famous study by Amgen. The scientists tried to reproduce the results for a particular cancer, 53 papers published in Science and Nature. They were only able to reproduce 7 of them. Now, that's not to say the other 46 were wrong, but there wasn't enough data on the methods or metadata, there wasn't enough information for them to be able to reproduce it. So the publishers have recognized that they're publishing a lot of useless junk, and so this is actually from Phil Campbell in Nature. There's publishers have got together and said we must do something about this, and so Nature and other publishers, and this is from their announcement, that they'll allow authors as much space as they like to describe the methods. That's something, and also you can attach the data behind the graphs and figures in the paper. So and they're now trying to give more data so you can actually have a real chance of reproducing the results. And I think this is a really important development. Chemistry. Okay, so chemistry was actually a project at my university, Southampton. Jeremy Frey was a chemist, and Simon Coles was another chemist who ran what was called the National Crystallographic Service. So this was their vision. You have a sort of lab which produced lots of results, you have databases, you have computer simulations, and you want to tie this all together. In those days, it was grid middleware. I would now say the cloud is a much better metaphor and a much better, more useful way of sharing storage and compute resources. But this was their eLab vision, and it was called the CombiChem project. And they also had a vision, and this was due to Liz Lyons at UConn, working with Jeremy, about the whole publication and data life cycle. So you have the experiments, publisher holdings, institutional archive, local web, peer-reviewed journals, preprints, technical reports, so the grey literature as well, digital library, virtual learning environment, so you can train undergraduates but also graduate students so they don't waste their time, and you can do the whole life cycle. So this was, I think, a very interesting vision, and I'm not sure we've really fulfilled that vision just yet. This is the National Crystallographic Service, and so they produce crystallographic data on relatively small molecules, and we set up a place for them to save it, and there was this eCrystals data repository where people could store the data, that you don't have to have it on a USB stick and just take it away to your lab, and then you forget where you've put it, all right? That's why I couldn't find my presentation at Bath in 2005, because it's on one of these sticks somewhere. Actually, not on these sticks, it's on a floppy disk probably, which I don't even have a disk drive. So I have some problems there. Okay, so that's what they did, and this is the sort of slide from Jeremy Frey, typical laboratory. Oh, I wish I knew how she did this. Getting numbers from this graph is really tedious. I have to go and measure it with a ruler. You know, I wish I'd recorded things in a different way, etc., etc. And so what they've developed from these early beginnings is an open source essentially electronic lab notebook. The problem with lab notebooks is that you can't search them. They're actually available on the shelf, but actually finding out what's there is very difficult. This is a way of doing it, preserving the record, and it's an interesting, exciting outcome. A view from Simon Coles on whether we've made progress. Well, he thinks, and it surprised me, the major advance is the usability of these tools. We now have Web 2.0 technologies, which is easy for people to go and start various things and get going immediately without loading huge amounts of middleware and stuff like that. And that actually is now being adopted slowly by most of the sort of scientific infrastructure. It's becoming easier to use. And that actually has engendered a culture change towards the adoption of standards and to enable integration, interoperability, and functionality. Everything can now be linked fairly easily by logical and very easy to use workflows. And the other comment he made was that mobile devices are on the verge of transforming the recording and doing of science. They have a nice slide of the two chemists in a bar drinking beer. Actually, they're working hard because they're interrogating with their mobile the lab apparatus. So mobile devices in all sorts of fields will, I think, be important. Okay, environmental science. This is almost my last example. But this was an interesting project, the NERC data grid project. Mark is here, so he can tell me when I go wrong. The British Oceanographic Data Centre and British Atmospheric Data Centre were where I got educated by Brian about some of the things about data curation. Brian was very insistent that he didn't want these things to be what he called worn archives, write once, read never. And so he believed that the curators absolutely needed to work very closely with the scientists as to what data they should save, what data they should throw away, etc. So this was their central activity. But the interesting thing to me, that this was quite clearly going to be central to NERC's, the Environmental Research Council's, major mission in delivering their science. But this wasn't core to their business. This was just a project that had a 3-year lifetime. So it was a slightly strange situation to me, that their NERC data grid was actually a project that could go away, even though it was core to their mission. But I think that's now changed. I have to show this slide. This was a project funded by JISC, and had Brian and also my wife was on this project, so that's why I have to mention it. It's called the Cladier project, and it was a very, very useful and early project about linking publications to data. And so this is an advert for their poster, and this is the one I'll be voting for, obviously. All right. So I recommend, the Cladier was a pioneer, and the poster is about the legacy of the ideas of Cladier, where they ended up, and it's extremely interesting. So the British Atmospheric Data Centre is now one of 4 centres in CEDA, Centre for Environmental Data Archival, right? That's a slide from Brian Lawrence. This is how things have evolved. They've also got software which are metadata objects for linking environmental science. There's a huge amount of complexity. It's necessarily international. You have to have standards. So this is implementing ISO standards for a data catalog. And so it goes from the observation and deployment to the data sets and so on. So large amounts of activity. And the data grid essentially has been replaced by what I would call Jasmine, which is, if you like, a hybrid cloud. So you have data, but you have data and computing resources in the same location. You don't have to move the data to the computing. And so this is a very interesting activity, and you can have resources locally, but if you need more, you can go up to the commercial cloud and use those. So this is where I think data grid ended up. What have we made progress? So this is from a friend of mine in Santa Barbara, Jim Frew, who he and Jeff Dozier set up the environmental program in Santa Barbara. And this is what he thinks. The biggest change in the last 10 years is, in fact, the funding agency mandates, the fact that they're asking you to make your data available. And so NSF's data management plan has made scientists pretend, perhaps, to take data curation seriously, but at least they have to have one, all right? So at least they have to think of something. And all my friends in America, when this came out in 2010, said, what's a data management plan? And I was able to say, go and look at the DCC website. It'll give you some examples. So I think the UK was well positioned on this. He does believe there are now better curated databases and metadata, but he's not sure, because there are many, many more data sets, whether that percentage has gone up. So is the quality fraction increasing? Not so clear. He also has 2 laws. Frew's first law, scientists don't write metadata. Right? Frew's second law, any scientist can be forced to write metadata, but it'll be bad metadata. So what he really believes, and this is actually relevant to this audience, is that you should automate as far as possible, but you can't do everything. And absolutely, scientists need to work with metadata specialists who have domain knowledge. Now, to me, that looks like a subject librarian, but we can debate that. So this is his view of what's happened in environmental science. I would like to say something about The NSF launched under its cyber infrastructure program, the DataNet program, which was about data. This is their major project called the Data One, Data Observatory Network for Earth. Bill Mitchener is the PI in Santa Fe. Albuquerque, actually. And what they are trying to do is to have the whole series. They actually don't archive data, so they have a number of data sets held by the organizers of the data set, and they store the metadata for that data set, and they offer services on that metadata. So there's this tool called the Mercury tool, which is, if you like, a federated search tool, which will take a subset of the metadata from each of these different data sets and give you a search across these different data sets who are partners of Data One. So that's the basic idea. I think it's too early to say whether anybody's actually using this service to find new science, but that's the hope, and we'll find out in the next few years. And they also have, again, provenance tracking. They have tools which will make the provenance of how did you get that result, what data sets did you use. They have tools to make those visible. So they have a number of interesting tools which I recommend. Microsoft Research, my group, produced an annotation tool for Excel, for example, where you could actually tell people what had been done to Excel. You could add annotations to it. So this is big JISC and little JISC, and I can't help but feel, but this has been slightly diminished from JISC, but JISC certainly did some pioneering work in the area of data curation and data management. And this is just one of them. This is a project keeping research data safe. This was a serious attempt to quantify how much it costs to keep data safe. And so this is just one of the project's cost-benefit studies, tools and methodologies focusing on long-lived data. So if you're a university or a project wanting to curate and save data for posterity, this gives you some idea of what the sort of costs and what you're going to have to do. And these are the sort of things, services that JISC provided wonderfully, had a whole series of wonderful data programs which were really pioneering. This is from the new JISC. This is another remarkable paper, which is called The Value and Impact of Data Sharing and Curation. So they looked at 3 services. One of the slides I had to remove was about the Arts and Humanities Research Council, which came into existence during this period, chose to cancel the Arts and Humanities Data Service, which seemed to me a real act of vandalism. But fortunately, the Archaeology Data Service survived. And so they've looked at that data service. They've looked at Economic and Social Data Service, ESDS, which is where I learned first of all about data curation, and the British Atmospheric Data Centre, BADC. And they looked at various ways to quantify the value of doing the curation, saving the data. And they saw very significant increases in research, teaching, and studying efficiency by using these data centers. The value to users exceeds the investment made in data sharing and curation via the data centers in all 3 cases. And by facilitating additional use, the data centers significantly increase the measurable returns on investment in the collection and creation of the data hosted. So I think this is a really remarkable study, and one that we should actually go and look at more closely. But this is the sort of thing that JISC does, and I'm pleased that JISC continues and is producing interesting reports. They've also, with Janet, which was set up by JISC many years ago, has now a framework agreement to provide data archiving. And so this is a way where there's guarantees, stored copies, indemnity insurance, ISO compliance, and Archivum, which is a spin-out from my university, Southampton, has been selected as a supplier, and there are people from Archivum here. You can talk to them about this. But this is actually another interesting development facilitated by JISC. So JISC is an important player. So I haven't got many more minutes left, so I better move on. Australian Research Initiative. Ross Wilkinson and Andrew Talor are involved in what's called the Australian National Data Service, ANS, and it was really to look at the Australian research data portfolio and to make it more valuable and reusable and so on. So 2006, they spent a lot of time. I spent most of my time, not most of my time, I spent a lot of time when I was doing eScience talking to various delegations from various countries, including Australia several times, before they actually didn't make the mistakes we made. They had a different program. They called it eResearch, and I think it was a really well-made, considered program, and it had in particular, in 2007, towards an Australian data commons. And in 2009, they set up ANDS, and it was to influence policy, inform best practice, and transform these individual collections into something that was really useful and internationally significant. So this is the sort of caricature slide, if you like. This is the sort of typical individual research, unmanaged, disconnected, invisible, single use, and you really want to do all these things to add value so searchers can easily publish, discover, access, and reuse it. So this is the sort of agenda for the audience of this meeting. And they have another interesting area. They have a budget and they can actually go and help universities. So this is example I'll give is James Cook University. It's right at the top near Darwin up in the north of Queensland. And it's in the tropical region. So they now have a tropical data hub. And with their other universities in tropical regions, they're a part of an international network of tropical data. And that really has put them internationally on the map with their data, and I think that's a very interesting development. So these are things that ANDS has been engendering in Australia. Open access, open data, open science. Well, Jim Gray firmly believed in this, as do I. And the example that Jim had, he worked on PubMed Central. He worked on making it a portable version, so that's why the version that's in the British Library and now PubMed Central Europe is actually based on stuff he developed with the NIH team, a portable version. And that's where the full text of the papers are meant to be put. And then from this, you can link to these various databases, and you can go around and go from the paper to the data, to different data sets, back to another paper, and so on. And you can really go and explore and do research in a serious way in this, if you like, a curated wall garden. So this is actually the National Library of Medicine. And of course, they have a budget of hundreds of millions of dollars per year. Now, not every field has that. So what we need to do is create something like this, which is not a walled garden where these are carefully curated. It's much more a Wild West. And that's a real challenge. And that's our challenge, I believe. And they have a tool called Entree, which does this cross-database searching. Okay. So that it was a voluntary compliance with PubMed Central. If you were funded by the National Institutes of Health grant, you should put your paper into PubMed Central, the full text. And that was 20% when it was voluntary. George Bush signed it into law in 2007, and as a result, the compliance rate went up to 75%. And then last year, the year before last, sorry, they said they would actually start delaying your next grant. Unless you'd put your papers in there, you wouldn't get your grant renewed. And as a result, surprise, surprise, there has been an increase. So it's now going up about 0.5% per month. And as of November, compliance had reached 86%. So I think you do need to have some sticks as well as carrots. Okay. And then in 2010, this has upset all my friends in America. What the hell's a data management plan? NSF required them all to have a data management plan. And of course, that was really a significant development. Even though I don't believe NSF can really monitor and actually see that they really do what they say, it's sort of fund and forget. But at least you have to say what have a lip service. So maybe it's the pretend, but at least it makes you think. And again, just to show, each of the research councils in the UK have now a data policy. This is the sort of general principles. Publicly funded research data are a public good. Specific data management policies to be discoverable, reusable. So they all have versions of this. This is the overall Research Council's UK data policy. But I think the big change, which, if you like, is the earthquake, was in February 2013 with a memorandum from the White House Office of Science and Technology Policy. Mr. Holdren sent out a memo directing all the funding agencies that they had to have a plan to support increased public access to the results of research funded by public money, your taxes and my taxes. And that was a principle they've now put in writing, and they also, besides the the textual publication, the paper, they also talked about the data, digital data as the record material commonly accepted in the scientific community to validate the research findings. So they talked about making the publication available and the data available. And just to finish up this section, this is the Engineering and Physical Sciences Research Council. They have a specific data policy, and their data policy is interesting for universities. If you get a grant from this agency, you're supposed to keep it securely preserved for a minimum of 10 years from the data. The person who developed it has privileged access for a number of years, and then after that, you have to keep it for 10 years. Who's going to pay for that? Who's going to do it? You know, these are issues, and the universities are obliged to come up with some idea by, I think it's May 2015. So they're going to be interesting areas, all right? It's going to really change things. So I think that's one of the significant things. Okay, the future. Just to finish up with a few words in my last few minutes. The Research Data Alliance. So this is an organisation funded by the European Commission, National Science Foundation, and the Australian National Data Service. And it's intended to research data sharing without barriers, is what its slogan is. And it's trying to build a community, social, organisational and technical infrastructure to reduce barriers to data sharing and exchange and to accelerate the development of what I think we all want. And they have an idea of working groups who will deliver not just reports, but actually things you can act on and things that you can adopt and make use of. Now, it's early days, and we'll see how they get on, but they have at the moment about 50-odd working groups and interest groups. Interest groups have not yet graduated to become a working group, and so it's very large numbers of people. So it's useful to group them into the solutions dimensions. There's a social, but there's also a technical, data providers and data consumers. And you can sort of roughly group these 50 working groups, interest groups, in these 4 quadrants, which sort of simplifies things. So that I think is a useful way of thinking about it. And you can find out more. This is an advert for the plenary, the 5th plenary in San Diego in March 9 to 11. So if you want to go, San Diego is a nice place. And this is a report that they've produced for the European Commission. The European Commission wants to know about jobs and growth, and this is the data harvest. Once you've got the data there, if you make it available in a curated form, it can be used by other academics for research. It can also be used by companies to start businesses. And so that's really the agenda. So this is a version of Surfing the Wave report, but this is a report which is not written by a scientist, it's written by a journalist so that politicians can understand the agenda. So you might find it interesting to read. Okay. Another interesting development is at the National Institutes of Health. They've now named Phil Bourne. He did the Protein Data Bank along with Helen Berman. He's now Associate Director for Data Science. That's really now a high-profile position at the National Institutes of Health. He has his own division, Associate Director for Data Science. And one of his initiatives is to set up what he calls a NIH Commons, which is connected digital enterprise for all the researchers funded by NIH. And he proposes to actually use cloud computing, most flexible, scalable, cost-effective infrastructure, implement as a federated hybrid cloud environment, enable public, institutional and private clouds and high-performance computing, because you want the computing next to the data, to interoperate. So this is at the very beginning. They're doing some pilots, but I think that's a significant development for the future. Okay, so this is my standard joke. You know, my students, when I was Dean of Engineering, never went into the library for library purposes. They chatted to their friends, had a cup of coffee, a warm place to work, used Wi-Fi. But you can do that in Starbucks in America, all right? So why do you need the library? Well, the library has a new role. If they wish to be central to the enterprise, they really need to focus on helping scientists meet these new demands. And I think that demands a change of role for the library, and I think they are now beginning to take up the challenge. So I'm hopeful that there will be somewhere here a place for the research library, that it will continue to be central to the mission of a university. At the moment, I think, because everything's online, Why do you need a library? And there are universities now being built without libraries. So if you look in your favorite search engine, my favorite search engine is, of course, Bing, all right? Sorry about that. But this is, a data scientist. Role of the future, the hottest job you've never heard of, the hot new gig in tech, mind, visualize, So this is I forget which date this was, but you can still find something like this. And this is Jian Qin from Syracuse. This is a slide she used, because everybody expects data scientists to do everything. And actually, it's not possible for anybody to know everything about that. And so I think it is worth looking at the role of a data scientist in a little more detail. And this is a slide from my colleague Kenji Takeda, who's at Microsoft Research Cambridge. And he distinguishes 3 levels. Data engineer, people who actually get the data from the satellite or the microarray or whatever and get it into some form, which can then be done by the analyst to go and find out the gene defects, to go and find out packages, scientific results. And then there's a data steward, which I think is where this audience comes in. So this is, if you like, one categorization of a data scientist. People will unlikely to be expert at all of those. So it is a collaborative activity. And so I like this slide from Brian Lawrence. How do we work? This is here. The red is the PI, standing on the shoulders of giants, namely the postdocs and the grad students who do all the work, all right? But actually in the future, he sees that actually that's a little more different, because we have the postdocs and grad students, and we now have software engineers and data scientists. And we need teams like that. And it's not clear, and I think this is a serious point, the culture change, it's not clear that the institutions have recognized that they need to have each of these things have to have a career path. That, you can't not value some of the people who are essential to do science. And so it's not just environmental science, which Brian was talking about, but also bioinformatics and other fields. We'll need to worry about career paths for all these people. Okay. I think it has been a tipping point, 2013. Besides the OSTP memorandum on open data and open publications, the Global Research Council, that's all the research councils, that's NSF, RCUK, the analogous organizations in France, Germany, Italy, Australia, around the world, came together, and they had a similar endorsement of a plan for open publications and open data. That was in May at the meeting in Germany. And then even the G8 science ministers also talked about the importance of open science and open data in June. And the European Parliament, as those of you who are European, everybody knows it's a slightly strange organization, but even they endorsed it. So I think this is actually a tipping point. We actually are going to have to go and worry about that thing, the access to data long term, and that's really what this conference is about. So just final comments before I get cut off by Kevin. These are from a paper I read from Michael Lesk. Helen Berman, who is the co-head of the Protein Data Bank, one of the most valuable resources in biology. It's the structure where you keep the structures of the proteins that you've actually figured out the structures. And this is someone in a blog praising her. One of the remarkable things about Helen is that her life has been devoted to service within science rather than, as some might call it, doing real science. Okay, so that really is a put down. She isn't doing real science. Well, actually, we're going to have to change that culture. And then, having talked about data, the importance of data and saving data, since 2004, I'm a little worried that we've actually been too successful. We don't need particle physics data to interact with archaeology data. It doesn't have to interoperate. We don't need to save all the data. And so we need to be thoughtful about what data we save and how we save it. And I like this thought, Michael Lesk quoting Bill Arms from Cornell, about just in time instead of just in case. So saving everything just in case is one way, but it's expensive. Most of the cost of archiving is spent at the start, before we know whether the articles will be read or the data used. With data, no emotional investment in peer review, it might be easier to do a simpler form of deposit, where as much as possible is postponed until the data are called for. There is, of course, some risk that a just-in-time system will leave us some years down the road with a data set which we wish we had curated while the creator was still alive. However, the longer the data has gone unused, the more likely it is never to be used. So I think, we need to be thoughtful about what we do and what data we keep. And so my last slide is, I think, what we need to do and why it's a noble endeavor. And it's this from Jim Gray's last talk. He had this vision of all scientific data online. You can go from the literature to the data, go back to put your own data, make a new paper, go back again. So the vision was very much formed for him for his work with the astronomers and with the National Library of Medicine. And what we need to do is not with a carefully curated set, we need to do it in the wild where we have repositories in different countries we have to put together. And so he believed, and these are his words, increase the scientific information velocity and a huge increase in science productivity. And I think we're not likely to see huge increases in research budgets, given this present austerity phase that the countries are in around the world. So I think we do need to make our science more efficient. And I do think it would be nice to have no excuse for researchers repeating the wheel because they didn't know about it. We need to make it so it's impossible for them not to know about it and to really name and shame if they do go and duplicate and do unnecessary research because they don't want to cite other people. So we do need to make this system work, and that's the vision of where we're going. Thank you very much for listening.
Thanks very much, Tony. We're running a few minutes behind, but I think we've got time for one, a brief question that's also capable of a brief answer. Tony, I can see one hand raised right at the back there. I'm afraid.
Okay.
There's a microphone on its way to you.
Hi.
Yes.
So in Ann Arbor, there's a repository called HathiTrust that charges people to put things in, and a repository called ICPSR that charges people to take things out. Which would you recommend for a new operation?
Well, it does. It does depend to some extent on what the funders give you. If the funders give you money to put things in, then you can pay that. The model of archive is that they look and see which universities have downloaded papers from archive, and they send a bill for a few $1,000s per year to each university library. And they'd managed to make that work. So I suspect it depends where the money comes from. There is a money in the university, it's called the library budget, and I think that we do not necessarily need to spend quite as much as we spend on journals at the moment, all right? And I think we're in a period of revolution. So I don't know. Those are great examples, and I think we need to find our way to an economic model. And I think the studies done by JISC are a helpful step, but they're only a step. And I, as you pointed out, those are two great examples, and I've only scratched the surface of some of the things that I know. And I apologize if I haven't mentioned your project. I do have one other announcement to make, though. Oh, is there another question?
There's one other question I'm going to
just over 200 years ago, the philosopher David Hume took the old canard that there was a distinction between the question why and the question how, and demonstrated very eloquently that actually why is subsumed within how. Thinking of the four paradigms, if you like, and some of the comments that have been made recently that argue that the role of theory in science is doomed simply because our capacity to demonstrate how.
Okay, there was an article by Chris Anderson, he's the editor of Wired, saying, who needs scientists in the age of Google? You've got all this thing, just use Google. Now, I have to say, I can think of nothing more stupid, right? That really seems to me absolutely stupid. So I absolutely disagree with that. I think scientists are necessary. I think you need all four paradigms. And I don't mean to, whilst I endorse the fact that we're moving into a phase of data-intensive science, it doesn't absolve us from understanding the theory and making cross-correlations between all of the paradigms. You need computing, you need the theory, and you need ultimately to test it with new experiments where you get more data. So I accept your comment, but I don't accept Mr. Anderson's the age of Google is sufficient, we can dispense with scientists. Thank you. I do, yes. I was going to thank Kevin. So it's an advert, really. It's for a popular book on computer science, right? So I'm going to give a copy to Kevin. He has to carry it around saying, what a great book, right? So Kevin, thank you very much for your invitation.
Well, thank you. Thank you.